Uh, a very good day to our lecturer, Dr. Lim Siew Ha, who taught molecular spectroscopy analysis, SQC7006. I'm from Group B for the assignment 2 that been assigned to us. My name is Rahman bin Maman. This group consists of Lim Fang, Tamirasi, anak perempuan Ganesan, Renita, Hari Krishnan, and Tianzang. The five of us will explain regarding the question given.
Hi everyone, I'm Ling Feng. I'm a full-time student from China. This is my part, how to calculate the double bond equivalent. Calculating double bond equivalent is an important step before analyzing of a function group, and it will give us more curious to narrow down the choices of function groups and make the task easier. It is a complex compound in the picture, and we can calculate the double bond equivalent in two ways. The first way is using DVE formula. Count the amount of carbon, hydrogen, and oxygen in the compound, then calculate according to the formula. The double bond equivalent of this compound we can calculate is 9. The second way is based on the structure characteristics of the compound. From the picture, we can see there are two benzene rings and a carbon double bond in the compound. The dB of benzene is 4. The dB of carbon double bond is 1. So the double bond equivalent of this compound is 4 plus 4 plus 1 is 9. Here is my part. Thank you for listening.
Hello and very good day to my lecturer, Dr. Lim Siew Ha, who taught molecular spectroscopy analysis, more on nuclear magnetic resonance spectroscopy, NMR. Okay, from we see here from this assignment, from this compound, actually they have similar chemical shift for this compound. As you can see, this compound have a similar chemical shift each of these two compounds. So from here, that I can detect about 1, 2, 3, 4, 5, 6 signal of this compound. Okay, firstly, I would like to assign a H8 compound here. H8 is easily detected because of the hydrogen on the carbon attached to the oxygen and are distributed due to the electronegativity of the oxygens. Here you can see easily 3.8 is assigned for H8 for methoxy group here. This is for H8. Meanwhile, for the aromatic, as you can see here, this is for the aromatic. H5 has been assigned to 6.797 ppm, and for the H6 is assigned at 6.9675, because and H2 also is assigned to 7.1785
This is because the hydrogen that attached to an aromatic ring in benzoid have a large chemical shift. Deshielded by the large anisotropic fields. And last, and for H7s, this is for the alkyl. Hydrogen attached 7 here has hydrogen attached to a double bond, vinyl hydrogen, are deshielded by the anisotropy of the adjacent double bond. And last but not least, here we have an OH bond. OH proton will be assigned at 7.651. My friend will elaborate more about this proton. Thank you. Hello, my name is Rahman bin Mamat. My matric ID 17 20 10 58. Okay, for carbon 13 signal from this compound, we can detect about 8 signal. This compound have a similar chemical shift from this one to this one. Okay, as you can see, I can label it carbon 1 here, carbon 2, carbon 3, 4, 5, 6, 7, and 8. 8 signal of carbon 13 NMR. Alright, as you can see, carbon 8 is easily detected on the signal is on 56.146 ppm here is easily detected for carbon 8. Okay, because the aromatic benzene here. Okay, meanwhile for carbon 3 and 4 is detected here. 3 and 4 range is 147.101 to 148.519. Okay, this is carbon 8. For carbon 1, here is attached to sp3, carbon 1 and 3 and 4. Carbon 1, 3 and 4, this is a quaternary carbon because there is no hydrogen attached to them. For carbon 2, carbon 5, carbon 6 and carbon 7 is located here. As you can see, carbon 5 is assigned at 109.738. For carbon 6 is assigned 126.935. For carbon 7 is assigned for 120.935 ppm. This is for carbon 7. Okay. For carbon 5 is auto for carbon 4 where it attached to OH. This is for electron donor group and more shaded. For carbon 2, this is auto for carbon 3 attached to methoxy group. This is electron donor group and deshielded. with the carbon 5. For carbon 6, one proton attached para to carbon number 3, and carbon 1 is a quaternary carbon. A 7 is a alkyl group. The range is from 100 to 170 ppm. My friend will elaborate more for this carbon 13 signal. Thank you.
Good morning, doctor. My name is Tamilara Sikenesen. My matrix number S20200210. Okay, I will explain what's meaning of HSQC and HMBC spectra that doctor provided. So how I say the peaks in proton and carbon NMR. Okay. My friend will talk about and explain more about COSI, and I will go for my second technique, HSQC. So HSQC is called as a heteronuclear single or multiple quantum. Multiple quantum correlation. So we see here the spectrum, 1J proton carbon 13 coupling. So means coupling between the proton and carbon. Okay. In other words, you can say which proton are directly attached to each carbon. So if we look at this HSQC spectrum, then by tracing across the x-axis, okay, which is proton, we are then going to be able to correlate one of these proton signal with something on this y-axis, okay, y-axis, which is a carbon 13 spectrum. Okay, so now the two spectra that we have that we correlating between are not the same. If we go down from this proton signal here, we eventually reach a peak. Okay, this is called as cross peak, okay, in the spectrum. If we go cross from there, you can see that it correlate to a carbon signal. Okay, so that is telling us this proton, okay, is directly attached to this carbon. Okay, this way this spectrum work. Each of these proton signal should only have one cross peak. Okay, because only one proton can only be attached to one carbon. Okay, so here from the spectrum they have 5 cross peak. Proton are directly attached to this carbon in this spectrum. So look at here, each 8 cross peak, we cross peak with C8. Okay, next we move to H2. Okay, before that I need to explain this one is H4, H2, H7, H6, H5 and H8. H6 and H7 almost look same. Okay, the line almost looks same. Okay, so just now I talk about H8, we cross peak with C8. Next I move to H2 here, we cross peak with C2. C2 is here, C2, this one is C2. Okay, then H5 we cross peak with C5 here. Okay, and H7 this one is H7. Okay, we cross peak with C7. Okay, we cross peak with C7. So H6 is cross peak with C6. Okay, so that is all from me for carbon 13 NMR spectroscopy. Next we move to next slide, HMBC. Thank you. Good morning, doctor. My name is Tamilara Sikenesen. My matrix number S20200210. Okay, we refresh back. What we learned the previous video. HSQC is one bond, the proton that bonded to the carbon. Okay, So this is our last technique, HMBC. First is COSI, second is HSQC, third is HMBC. So HMBC is heteronuclear multiple bond correlation. Is a correlation between nuclei of two different types that are separated by 2 or 3 bonds. Definitely no same with COSI. And the previous version is called as colloid. Okay. The purpose of HMBC, for what purpose? Anyone know? Okay. Okay, I give answer. Okay, carbon and proton. Carbon HMBC is frequently used for assigning of quaternary and carbonyl carbons and thus connecting spin system. Okay, so you can see from previous HSQC video, I only have 5 cross-peak, but here we have more than 5 cross-peak. Okay, and then here the previous HSQC you can't able to view C4, C3 and C1, but here complete. Okay, this spectrum. I already label all these. Later I explain. Before that, this one is a proton, this one is a carbon, this one is a H4, H2, H7, H6, H5, this one is a H8, this one is C8, this one is solvent, this one is a C2, C5, C7, C6, C1, C4 and C3. Okay. Okay, so they have 4 cross-peak that are not related with carbon and no correlate with carbon and proton. 1, 2, 3 and 4. Okay, we just ignore lah. So next we go for H8. H8. So correlation with C3. How you know this is C3? How? So we, as I say, we must read from proton to carbon. So this one is a proton, H8 to C3. So this is the last one, C3. So we go for here, H4 correlation with C5 and C3. As I just told you, just this one is a C5 and this one is C3. So they have another 3 nice cross-peak here. H2 correlation with 3 nice peak, C7, C6 and C4. Okay, next move to H7 correlation with C2 and C1. Okay, and then H6 correlation with C4 and C6. Let's jump to the H5. H5 correlation with what? Okay, correlation with C5 here and C3 here. Okay, what's mean here? J, 3J, 2J. What's that? That's the symbol of bond away. 3 bond away, 2 bond away. This is symbol. Okay. 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 After label all this, we look this structure. Okay, one by one we check one by one. Okay, let's start from H4. Okay, H4, this is H4. This is H4. So how many bonds away? They have 2 bonds away. So how you know it's 2 bonds away? So 1, 2, 1, 2. Okay, go for the H2. H2 is here. How many bonds away? They have 3 bonds away. How? 1, 2, 3. 1, 2, 3. Okay. So H6, how many bonds away? 1, 2. Okay. Okay, H5, 2 bonds away. 1, 2. Okay, H8, how many bonds away? 1, 2, 3. Okay, so you can see no 1, 4 and 5 bond. Okay, correct, right? Okay, after checks all this cross peak, we realize the structure all match. Okay, therefore the assignment is confirmed. Okay, thank you.
Good day, doctor. My name is Renita Hari Krishnan and my matrix number is S2020465. This slide is the interpretation of carbon NMR spectrum. In this spectrum, observation of 30 ppm and 206 ppm with the given multiplicity draft a solvent peak of acetone. Apart from this, counted line in carbon-13 NMR indicate that there is 8 types of carbon environment. As we know, this is because each unique carbon gives a different line. A carbonyl carbon C3 is highly deshielded compared to C4 and is absorbed furthest downfield, where it is because of deshielded by the presence of an electronegative element of oxygen. While carbon-8 is alkyl carbon with oxygen attached, sp3 hybridized rise signal at 56.146 ppm due to little anisotrophic effect of aromatic ring. A diamagnetic anisotropy causes the carbon atom signals of the aromatic ring is a decreasing order of with the carbon 1, carbon 6, carbon 2 and carbon 5 to appear lower field strength. Carbon 7 at 120 ppm by a diamagnetic anisotropy, where carbon atom attached to double bond is deshielded by the effect of non-uniform magnetic field produced by the presence of pi electron. Type of carbon determined with carbon 1, 3 and 4 is a quaternary carbon with no proton is attached, while carbon 2, 5, 6 and 7 is a methane carbon where only one proton is attached. Carbon 8 is a methyl carbon attached with 3 protons. Move to the next slide with the interpretation of proton NMR of the given compound. In general, aromatic compounds have two types of hydrogen. Hydrogen which are directly attached to the benzene ring, and the other types are benzylic hydrogen which are attached to carbon atom attached to benzene ring. Hydrogen attached to the benzene ring have a large chemical shift, usually in the range of 6.5 to 8 ppm. The hydrogen on an aromatic ring are highly deshielded than those attached to normal double bond due to the large anisotropy effect generated by the circulation of the pi electron of the benzene ring. Benzylic hydrogen are also deshielded by the anisotropy effect of the pi system, but the effect is smaller due to the more distant from the ring. On the other hand, the electron donating group like methoxy increase the shielding of ring hydrogen, causing them to shift towards a filled region of proton NMR spectrum with 3.882 ppm. This group is highly shielded to that attached hydrogen by donating electron density to the ring through resonance interaction. Hydroxy group is attached to the benzene ring in the electron is also electron donating group, which activating the benzene ring. This means that electron density of the benzene ring is high. However, a six-member ring intramolecular hydrogen bond in the latter compound, it is a part responsible for its lower field shift. The more acidic hydroxy group of phenol generates a lower field resonance, therefore forms signal at 7.65 ppm. Hydroxy group activate ring by adding electron density to the ortho and para proton. Thus, proton in carbon 5 and carbon 7 chemical shift move upfield with decreasing ppm because of increased electron density with compared to carbon 2 proton which located in meta position. In aromatic ring, coupling usually occurs beyond the adjacent carbon atom. The ring hydrogen which are chemically as well magnetically non-equivalent interact with one another to produce spin-spin splitting pattern. The extent of interaction depends on the distance between them. The closer the proton is to the other hydrogen atom, the greater the effect on the proton. For the ortho position of the benzene ring, the coupling J value will be higher if a hydrogen atom is present. Ortho hydrogen couple more stronger than meta hydrogen. The proton in carbon 5 has an ortho coupling with proton in carbon 6 with 8.8 Hz. The proton in carbon 2 had meta coupling with proton in carbon 6 with 2.3 Hz, while the proton in carbon 6 had meta coupling with proton in carbon 2 and ortho coupling with carbon 5 with 8.0 Hz. The overall information retrieved from the proton NMR and carbon NMR were tabulated corresponding to the each assignation. That's all from me. Thank you.
Hello, doctor. I'm Tian Zhang. I choose the question D, that is, show the observed causative correlation on the structure above. As we know, causative correlated spectroscopy is a useful method for determining which signals arise from neighboring protons, which up to 4 bonds. Correlations appear when there is spin-spin coupling between protons, but where there is no coupling, no correlation is expected to appear. First, let's see this structure. We observe that 7 bond, an imaginary line, observed similar point in present at opposite direction. It means to equal distance but opposite direction, and an equivalent group are founded. In combination, a combination of one-dimensional and two-dimensional NMR experiments are necessary for complete confidence in chemical structure. The first step in structure characterization is one-dimensional proton NMR. The chemical shift, multiplicity, coupling constant, and integration are all factors to consider when assigning protons. And the remaining protons are doublets, triplets, and multiplets that can be assigned by two-dimensional causative. Correlation spectroscopy causative shows the correlation between hydrogens which are coupled to each other. In hydrogen NMR spectrum, the spectrum is plotted on both 2D axes, while 2-bond and 3-bond coupling is easily visible by causative. Long-range coupling can also be observed with long acquisition times. The cross peaks not on the diagonal that are symmetric to a diagonal shows causative correlations. A one-dimensional spectra determined by frequency axis chemical shift has been converted into a two-dimensional spectra in which two frequency axes corresponded to chemical shift, and different protons have signals at their respective polarization frequencies peak. It's not difficult to imagine that in frequency domain, the signal peak of two-dimensional spectra appear on the diagonal of the square. The signals which larger chemical shift are distributed on the lower left, the diagonal of the two-dimensional spectrum, and the signals which have smaller chemical shift are distributed on the upper right square. Any regulation of the signal size, such as coupling interaction between spinning nuclei, appears on both sides of diagonal in the form of cross peaks. The characteristic of spectrum is that peaks on diagonal corresponded to one-dimensional spectrum, and the sigma value of cross peaks outside diagonal in F1 and F2 The mix corresponded to the chemical shift of the coupling nuclei, providing information about hydrogen and hydrogen coupling through triple bonds. Each cross peak is made of a vertical line and horizontal line parallel to F1 and F2 axes to obtain chemical shift of two mutually coupled nuclei. So the cross peaks, the correlation of each coupling hydrogen can be established. Off-diagonal peaks indicating coupling between the two protons. The way to analyze cosine spectrum with many ion-assigned protons is to make a table of correlation like the one seen here. In this structure, all assigned protons show the cosine correlation. That's all. Thank you so much for listening.